Thank you for introduction. I'm Shogo Yamada. I'll talk about pseudorandom function-like states from Common Haar Unitaries. This is a joint work with Minki Hhan. First of all, I will talk about the motivation from cryptography. The ideal goal of cryptography is constructing useful cryptographic primitives. For example, obvious transfer, secret key encryption, message authentication code, zero knowledge proof, bit commitment, multi-party computation. But most of these primitives need unproven computation. Most of these primitives need unproven computation assumption to achieve their securities. In the classical world, all of these primitives need one-way functions. Here, one-way function is an efficiently computable function, but it is hard to invert efficiently. But the situation becomes different in the quantum world. In the quantum world, we can construct these primitive from pseudorandom function-like state generators. I will call it these PRFSGs for short. Pseudorandom function-like state PRFSGs is the following algorithms. So it is a quantum polynomial time algorithms which takes on secret key k and bit string x and output a pure state phi k of x. For security, roughly speaking, if adversary doesn't know the secret key k, each phi k of x is computationally indistinguishable from Haar random states. More formally, we consider the following security game. In this security game, adversary can query this oracle gk. If adversary queries x to this oracle output quantum state phi k of x, which is the output of these PRFSGs. So if we replace this oracle with ideal one, so namely if adversary queries a bit string x, it outputs Haar random state theta x for each x. So for security, we declare these two situations are computationally indistinguishable. So as I mentioned, we can construct many useful cryptographic primitives from PRFSGs. And also, PRFSGs can be constructed from one-way function. On the other hand, in some sense, it is known that we cannot construct one-way function from PRFSGs. So namely, one-way function is not necessary for constructing PRFSGs. So therefore, PRFSGs could exist even if we don't have one-way functions. But for now, we don't know how to construct PRFSGs without one-way function. So actually, we lack a concrete assumption for constructing PRFSGs without one-way function. So therefore, instead of concrete assumption, we consider an idealized model in which one-way function seems not exist. So in this work, we show that PRFSGs exist in the quantum Haar random arc model. I will call it a QHRO model for short. So the quantum QHRO model is introduced by these two papers. And also, in this model, anyone can use the Common Haar Random Unitary as a public resource. So namely, there is a trusted third party who can evaluate a Haar Random Unitary U, and then honest party can query to the Haar Random Unitary U, and also any adversary also query these Haar Random Unitaries. So in the definition of PRFSGs in QHR model is similar to the in the plain model one. The difference is that both a generation algorithm G and adversary can query the common Haar random unitaries. So we consider the following security game. So the adversary can query generation algorithms. These generation algorithms can use a common Haar random unitary, and also adversary can query this common Haar random unitary U. Even if we replace this generation oracle with ideal one, and also adversary can query the common Haar random unitary, we declare that these two situations are computationally indistinguishable. So our construction is as follows. So let's divide a secret key k into two parts, k0 and k1. And then our construction is as follows. First, prepare for input secret key k and bit string x. It prepares ket x and then apply power x depending on k1, and then apply common Haar random unitary u. Then apply power x with respect to this k0. So we show that non-adaptive security and adaptive security based on different techniques. So I will share each technique now. First, let's share the non-adaptive securities. So for showing non-adaptive security, the goal is as follows. For any bit string x1 to xl and any fixed state ket psi, this real state is close to this ideal state. Here, in this real states correspond to the adversary's state if adversary queries generation oracle non-adaptively. And also this phi k of x is our construction, and the ideal states correspond to the adversary's state when adversary queries generation or ideal oracle and common Haar unitary non-adaptively. And also this each theta I is independent Haar random states. To show these two quantum states are close, main challenge is how do we estimate the expectation of u? So in some case, we can by using a previous technique, we can show the expectation of Haar random unitary u, but such technique might not useful for our case. So therefore, we show that a new approximation formula for this Haar twins. So the Haar twin approximation formula we show is as follows. So let D be a dimension of unitary, and then for any quantum state rho, the Haar twin on quantum state rho is close to the right-hand side. So if this t square over d is negligible. Here, each phi is a permutation over t elements, and then it acts as follows. So it permutates t registers. So to show this, I can't share its detail because to show this, we need a Weingarten calculus from random matrix theory. But by applying it, we show that these theorems. So to show that non-adaptive security, it suffices to apply this theorem to the previous this one. Here we need to demark on concurrent work. So in the similar result is independently and concurrently show in the context of to construct unitary designs or pseudo-random unitaries. Next, I will share the technique for proving adaptive security. So to show adaptive security, we consider the following hybrid. First one is corresponding to a real experiment. So namely, this U is a common Haar random unitary, and this VKU is unitaries which implement our PRFSGs. Our goal is to show this real experiment is close to this one. So here we replace each query to VKU with independent Haar random unitary W. Here we consider the classically secure PRFSGs namely adversary can query generation oracle classically. So, but the adversary can query a common Haar random unitary quantumly. So, namely, adversary can query any state to common Haar random unitaries. So, therefore, each query to U could be a quantum query, but we restrict each query to VKU and W is classically. So, to show this, first we consider the following intermediate hybrid. In this hybrid, the first query to U is the same, but we replace after the first query, we replace each query to U with U dash. This U dash is a U with minor modification. So to show this, we show that following unitary desampling lemma. In this lemma, we consider the following security game. In the first stage, adversary can query to challenger to query her random unitary U, and then adversary outputs two distribution D0, D1, and this distribution is a distribution over quantum states. And the phase 2, challenger choose a bit B uniformly, and then if B equals 0, challenger sets this U0 as original her random unitary U. If B equals 1, challenger sets U1 as a U and swap alpha beta. Here, alpha and beta are quantum states sampled from D0 and D1 respectively. And then swap alpha beta is a swap unitary, just swaps quantum state alpha and beta. If the input state is orthogonal to both alpha and beta, it acts as identity. And then adversary can query to this UB, and then adversary outputs B dash to distinguish the B equals 0 from B equals 1. So if adversary queries at most polynomial time, any adversary cannot distinguish the case when B equals 0 from B equals 1. So we can apply this unitary desampling lemma to our case. So to apply this, we can view that this hybrid, we can divide these two hybrids into two parts. The first part is a first query to U. We can view this part is phase 1. After the query, we can view it is phase 2. And also here, alpha and beta is defined in this way. So, but for now, you don't need to care about this alpha and beta. So by just applying unitary desampling lemma, we show that this H0 is close to H-0. Next, we introduce a new intermediate hybrid, H-0. In this hybrid, we replaced first query to VKU- with independent her random unitary W. Here, we need the detail of alpha and beta. Here, the alpha is sampled in this. Alpha is sampled for some fixed x and k1. Here, k1 is corresponding to this secret key k. And here, x is query to VKU by the adversary for the first query. And for the distribution D1 is just a Haar measure. So namely, it just output her random state. So since x is a next query to adversary, when adversary queries x to this first VKU- or W, it just outputs the same states. So namely, we can replace the VKU-x with Wx for independent Haar random unitaries. So therefore, we can show that this trivially implies that H-0 is close to H-0. So, but here we need to replace these after the first stage. We need to replace all query to U- with original U. To do so, we introduce the following hybrid H1. Here, we replace the second query to U, first query to U-. We replace the first query to U- with original Haar random unitary U. To show this H-0 is close to H1, we need the following unitary reprogramming lemma. So in this lemma, consider the following security game. So in this game, first adversary just outputs some unitary U and some algorithm C which reprogram U. And in the next stage, challengers choose bit B uniformly. And then if b equals 0, set u0 as u. If b equals 1, by running this deprogramming algorithm C on input u, then output u tilde. Then set u1 as u tilde. In the next stage, adversary can query to this ub. In the phase 3, adversary does the query to the ub, but challenger sends the information on u tilde. By using the information before phase 2 and this u tilde, adversary determines whether b equals 0 or 1. So if adversary queries in phase 2 at most polynomial time, we can show that adversary cannot distinguish b equals 0 from b equals 1. So we can apply this deprogramming lemma for our situation. First, the query to u and w can be seen as phase 1. And the first query to u dash or second query to u can be seen as phase 2. And after the query to oracle can be seen phase 3. So this fits our unitary deprogramming lemma. So we can show that this h dash dash 0 is close to h1. So here we get this h0 is close to h1. So by considering similar hybrid, we get that this real hybrid h0 is close to ideal experiment HP. So therefore, we can show that security of our construction. So this is an overview of our proof. So let's summarize our work. So in this work, we construct PRFSGs in the quantum Haar random oracle model. And also its construction is very simple. It's just apply Pauli X, then apply Common Haar Random Unitary, then Pauli X one more time. Here we need to mention concurrent work and announce Bostanch, Gurtai, Din independently and concurrently construct pseudorandom unitaries in the inverse-less QHRO model. Here, inverse-less means that adversary can query U only itself. On the other hand, in our situation, adversary can query U and its inverse. After our work, they continue their research, and so they construct PRU in the quantum Haar random oracle model. So, namely, they upgrade their security into QHRO model. So I want to mention interesting open problem. First one is what we construct PRFSG's QHRO model, and also after our work, PRU is constructed in the QHRO model. But another primitive could be constructed in QHRO model. So my question is, can we construct other primitives in the QHRO model? So for the next open question or next further direction is, can we use oracle separation? Can we use our QHRO model for oracle separations? This is also an interesting open question, I think. So that's all. Thank you for attending.
Questions? Yeah, go ahead, sir.
So I have three questions. So first question was on R12. Actually, I wanted to know can the R12 approximation formula
Yeah.
generalize to mixed states and other groups like three-quarter symmetry?
Sorry, please say again.
Can the formula can generalize to any mixed states or any group section like three-quarter symmetry?
I think in this proof, we use Weingarten calculus for Haar random unitaries. So if we consider another group, for example, Clifford group, we need to use Weingarten calculus for Clifford groups. I think if the for example, if Clifford Weingarten calculus for Clifford group satisfies a good condition, which for example, it satisfies the good property I used in this proof, then we might show the similar result for other groups.
And for the future scalability, like what are some other cryptographic primitives that can be implemented using KHR?
So,
for example, any kind of primitive that you can use?
for example, I think so. For example, some primitives, I think, for example, quantum so some cryptographic primitives which only uses quantum computation, but which don't use quantum communication. For example, some cryptographic primitives with Q quantum computation, classical communication primitives.
So, quantum inspired?
Yes.
I'm sorry, I joined a bit late. So, the PRFS construction is going into this Oracle models, right?
Yes.
But PRFS constructions are known no Oracle models. What was the motivation?
Yes. So to construct PRFSs in the prime model, we need some computation assumption. For example, if PRFSTs exist, if PRFSTs exist, it implies PQP is not equal to PP. So therefore, to construct PRFSTs without any assumption is a challenging problem. But by considering this idealized model, we show that our construction satisfies security without any additional conditions. So it's a motivation of our work.
Okay, so you're providing this hardware unitary, like providing a random function.
Yes.
So, yeah, so then if you have a random function available, then you have PRFS.
Yes. But in the if we consider our motivation is constructing PRFSTs without one-way function. So if we consider, for example, random oracle model, we can construct PRFSTs. But in that model, one-way function also exists.
You can close the finish.
Yeah. Yes. So my motivation is to explore the whether PRFSTs are achievable with that one-way function or not explicitly.
Go ahead, sir.
Doing an oracle based on how random unitaries will activate an exponential runtime for each individual query.
So space again?
The oracle is based on a high random unitary.
Yes.
So to create a high random unitary, you need exponential time.
Oh yes, so that's a problem here. So, but in this model, we assume that some trusted party can generate a Haar random unitary or some unitaries which is indistinguishable from Haar random unitaries efficiently.
But like how many moments do you need?
For example, so adversary queries are at most polynomial times. So, for example, we need some instantiation that this u is close to a Haar random one for any polynomial moment.
So do you need like a 2 design, 3, 4, how many? Like, if you're not using a high random unitary, do you need to be a design?
Yes, but this design, if we consider T design or something like that, T design is to construct T. So if adversary queries at most T plus 1 time, the security doesn't work because T design doesn't require the T+1 moment is close to Haar random 1.
So, but if you try to replace the random unitary by a pseudorandom unitary, then you are assuming a PRU construction.
Yes.
Assuming PRU and then dictating a PRU.
Yes, yes.
The PRU is wrong.
Yeah.
So, what are we doing?
For example, if we find a good instantiation of this QHR model, for example, for example, we use some random circuits for this U. If the random circuit satisfies a good property, for example, satisfies a good property, I believe that it is a good instantiation of QHR model.
So, in some sense, you're giving a reduction from PRU to PRU.
Yes, so if PRU exists, we don't consider these models because we can construct PRFSGs from PRU.
Good.
It's not got the concept of adversary. So, is it related to adversarial quantum attacks? Something like that?
Sorry?
So, I did not got the concept of adversary which you mentioned in the slides. So, is it related to the adversarial quantum attack? Something like that?
Here, so we only consider the classical query secure of PRFSGs. So in that model, the bursary only queries PRFSG oracle in classically. So this is not so LOC situation. So it's just we require the securities.
Okay, maybe one last question.
Just clarify something in your unitary programming lemma slide. Yes.
Yes.
So what is that again?
This C.
What
So C is some algorithms on input unitary and the output some new description of unitaries. So it's just a deprogramming algorithms for this unitary U. Yeah, so to show this, we need some idea from post-quantum random permutation model. So, but its proof seems very complex, complicated. So I can't share it here.